This is a solution to a problem that we were working in our question and answer session for the Honors Calculus 1 class. And it was in the Applied Optimization section, which is section 4.7 in the Larson and Edwards calculus textbook with early transcendental functions. This is problem number 24. So here's the problem statement. It asks us to find the area of the largest isosceles triangle that can be inscribed in a circle of radius 6. Now they didn't add this coordinate system. I added a coordinate system though. Since it's a circle of radius 6, I think the easiest way to describe that circle is to place it in the xy plane with its center at the origin. Other things that I know, when I'm on a circle of radius 6 centered at the origin, x squared plus y squared is equal to 36. And I'm asked to find the area of the largest isosceles triangle that I can inscribe in this circle. So we're trying to maximize the area. And they ask us to approach the problem in two ways. First, they ask us to write the area as a function of h, where h is this distance from the x-axis to this lowest point on the triangle. My triangle is not very symmetric. It's supposed to be symmetric. This is an isosceles triangle. This angle and this angle are supposed to be the same. In the textbook, they've labeled that angle alpha. And we know that the distance from here to here is 6 because it's inside a circle of radius 6. Okay, so first they ask us to solve this problem by writing the area as a function of h, which seems to be a pretty unusual choice, but that's okay. And we know we're trying to find the maximum area, so that's our objective function. Let's see, the first thing we want to do, the first thing we always do is we, sketch the region. So we are sketching the triangle inscribed in the circle. Want to sketch whatever is given to us. They told us this, and they also gave us this picture in the book. So you want to visualize what's going on. And then when we're doing applied optimization problems, the next thing we want to do, is identify the objective function. And the objective function in this case is area. And it's area of a triangle. So I've got 1/2 base times height. I'm using capital H and capital B because I've used lowercase h for something else. And they're asking us first to write the area as a function of h, where h is this distance from the x-axis, and then asking us to optimize the function. And I think we can all see that if our triangles, if h were, or if this side were not below the x-axis, I'd end up with triangles like this. Oops. That's not going to have maximum area. The maximum area of a triangle, an isosceles triangle inscribed in this circle, will have a distance h like this where h is positive, because we know that the area of this triangle is obviously bigger than the area of that triangle. Okay, so we're trying to maximize this. We've identified the function that we need to maximize, but we're in calculus 1. So this needs to be a function of a single variable only. And the problem statement actually asks us to write it in terms of this variable, not either the base of the triangle or the height of the triangle. So we need to write the base and height of the triangle in terms of this little h right here. Now the base is this distance from here to here, and the height is that distance from there to there. The height is actually pretty easy. It's this 6, that distance 6 from the origin out to that the outermost point on our circle. That's 6 plus h. And the base is x over here times 2, because if this is the distance x and this is the distance x, I'm going to double it. So it's 2x, where xy is a point on this circle. X squared plus y squared equals 36. Now I can't use 2x here. I need to write x in terms of h so that I can get area entirely in terms of h. But I can find x in terms of h using this equation of the circle. When we're at this point, I know it looks like it's tilted, I'm sorry. X is just given by x, and the y value is not h is a distance. Y is going to be negative h. So if that distance was 1, y would be negative 1. That distance is 2, that y would be negative 2. So x and negative h satisfy the equation of the circle. So I can take this, simplify it, negative h times negative h is positive h, and then just solve for x. So x turns out to be square root of 36 minus h squared. Now I've got the height of my triangle in terms of h and the base of my triangle in terms of h. So I can write this area as a function of h only. And that's always what we do. We identify the objective function, which happened to be area, and we identified that using the problem statement. We wanted the area of the largest isosceles triangle, so we wanted maximum area. But then we need to write it in terms of a single variable because we're in calculus 1, and we can only optimize functions of a single variable at this point. Okay, so I've got area is 1/2 of the base times the height, and the base is 2 times the square root of 36 minus h squared. The height is 6 plus h. The 2's reduce, and it will probably be better to write it this way. For when we take the derivative in a little bit. So now I've got area as a function of h. At this point, it's pretty easy. It's a straightforward problem. There's a lot of algebra involved, but it's pretty straightforward. If I want to maximize this, I need to find critical points, figure out where the slope is 0, figure out where the slope is undefined. Once I know where the slope is 0 and where the slope is undefined, then I can solve for or I can determine, excuse me, whether each of those critical points corresponds to a minimum or a maximum value of our function. So we've got area as a function of h. Next thing we want to do is we want to optimize that. So we want to find the critical points, which means computing the first derivative. You want to set the first derivative equal to 0 and solve for h. You also want to consider values of h that make the derivative undefined. And we also have to consider the application that we're dealing with here. There are only certain values of h that make sense for our problem. So I've got this right here. I'm taking the derivative with respect to h of this product according to the product rule. That's my first function and that's my second. We'll have the derivative of the first times the second undifferentiated plus derivative of the second times the first. I usually like to write that derivative in a different color, and I forgot to this time. It's okay. Derivative of 6 plus h is just 1. The derivative of this guy requires the chain rule because I've got a function nested inside another function. So we'll do derivative of the outside. Derivative of a function to the 1/2 is 1/2 of that function to the negative 1/2 times the derivative of the inside. And the derivative of the inside happens to be negative 2h. So that's derivative of the first, and then we're multiplying by the second, and then we're adding derivative of the second, which happens to be a 1 times the first. And of course, the 1/2 and the 2 reduce. We end up with this. Now this expression to the negative 1/2 can be rewritten. Remember, if you've got a negative exponent, it's 1 over the same thing, but you change that negative exponent to a positive exponent. So that's what we're doing here. So I'm going to change that negative 1/2 to a positive 1/2 and put that in the denominator. And then in the numerator, I still have a negative h times a 6 plus h. And over here, I've got 36 minus h squared to the 1/2. Now that it's written as a fraction, remember what our goal is eventually. We're trying to find critical points. We're trying to find those points on the graph where the derivative is 0. So that means we'll have horizontal tangent lines, or maybe where the derivative is undefined. Because we know where the derivative is 0 or where the derivative is undefined, we could have a minimum or a maximum there. So we've computed a prime. That part wasn't too bad. It's just the product rule with the chain rule in it. But now I want to set it equal to 0 and solve for h. Since I had this negative exponent, it was helpful to rewrite it as the same thing but with a positive exponent. So we rewrote it with that expression in the denominator instead of the numerator. And now we want to get a common denominator. And again, the reason why is because we're about to set a prime equal to 0 and solve for h. It's easier if we can just write it as a single fraction. So we'll remember that that is itself over 1, and we'll get a common denominator, which is just this guy right here. And we multiply. You can distribute in the numerator. Over here, you've got something to the 1/2 times the same thing to the 1/2. You can think of that a couple of different ways. You can think of it as a square root of something times itself. Square root of a times square root of a is square root of a squared, or just a. Or you can think of that as an exponent property. You just add the exponents. 1/2 plus 1/2 is 1. So we will have this 36 minus h squared to the first in the numerator over here. And they have the same denominator now, so we can write them together. I've got that right there. Okay, and we want to simplify this. I've got a negative h squared and a minus h squared, so that's negative 2h squared, and then a negative 6h and a 36. Very close to being ready to set this equal to 0. And I want to factor out that negative 2. We had negative 2h squared minus 6h. So we factor out the negative 2, that's going to give us a 3h. And we also had a positive 36. Yeah, positive 36. And when I factor out a negative 2, I get a negative 18. And we can factor that numerator further. two numbers that multiply to give me 18, or negative 18, that add to 3 are 6 and 3, if the 6 is positive and the 3 is negative, because 6 times negative 3 is negative 18, and 6 plus negative 3 is positive 3. Okay, so A prime is completely factored. Now we're ready to set A prime equal to 0 and solve for H. I've got a fraction, it equals 0 whenever its numerator equals 0. Of course, the negative 2 is never equal to 0. The only way this product is 0 is if one of the factors is 0. So we solve each of those for H. Okay, so those are critical values of the function A of H. We should also keep in mind where A prime is undefined. This is undefined whenever 36 minus H squared is positive, or excuse me, is negative. This is negative whenever the absolute value of H is greater than 6. Yeah, but let's think about the domain for this particular problem. If I was working with just A of H, just a function of H, and I had no application, if I wanted to optimize that function, I'd have to keep H equals negative 6 and H equals 3 in mind. I'd have to think about whether whether these values are in the domain of the original function A of H. And I'd have to think about this expression and think about whether or not there are any H values for which this is undefined that are in the domain of the original function. We would do that every time. But in this case, we're looking at an application problem. We're trying to find the area of the largest isosceles triangle that can fit in this circle. And we're saying that H is this distance from the x-axis. Now, if H is the distance from the x-axis, and we're going to say, we've assumed that this triangle has to go below the x-axis because these triangles up here have smaller area than this triangle down here. Since this bottom edge of the triangle has to go below the x-axis, we're saying that H has to be positive. But just from this picture, we see that H has to be positive, but H can't be greater than 6. Because if H were greater than 6, we'd be going outside of the circle, and that doesn't make any sense. H can't even equal 6, because if H were equal 6, we just have a line going up and down. We wouldn't even have a triangle. If H gets very close to 6, like let's say it's 5.9, we get a very tall, skinny triangle. But if H were equal to 6, we wouldn't get a triangle at all. It would just be a straight line segment from the top of the circle to the bottom of the circle. So H has to be between 0 and 6, given the original assumptions of our problem. So we set A prime equal to 0, we solve for H. If you want to consider values of H that cause A prime to be undefined, those are critical points as well. Yeah, and we're only interested in values of H that are in the implied domain. So we need to identify the domain that makes sense for our problem. And given the discussion that we just had, looking at our picture, we said that H has to be between 0 and 6. It's possible that H is 0. Probably not, but it's possible. but it definitely can't be 6, but it's not going to be negative 6. So that's out. And this expression is undefined. When this expression under the radical is negative, because we can't take the square root of a negative number in the real number system. We could take the square root of 0, but it's in the denominator. We can't divide by 0. So a prime will be undefined when this is true. And that means that 36 is less than h squared. And that happens when the absolute value of h is greater than 6. And I'm not going to go into the details of that. If you want to talk about that, we can talk about why that's true. Just very briefly, here's what y equals h squared looks like if we're using h instead of x. Here's 36. Y equals 36. Solving this inequality, 36 is less than h squared, is asking for all the points on this graph when h squared is greater than 36. So it's out here. And that corresponds to 2 intervals. One is from negative infinity to 6, and the other one is from 6 to infinity. Okay, I said I wasn't going to go into it, but I still did. So a prime is undefined out here, but that's not in our implied domain anyway, so we don't have to worry about it. So it looks like we only have one critical value in our implied domain, and that's h equals 3. So we just need to determine if h equals 3 corresponds to a minimum value or a maximum value. You can use either the first derivative test or the second derivative test. I think I want to use the first derivative test because I've already factored a prime. It's not to solve for h. We're using the first derivative test to find relative extrema. Okay. So a prime looks like this, or we could make a number line for a prime like this. Normally I would go from negative infinity to infinity if that was the domain of my function. But the implied domain, the realistic domain for this word problem is 0 to 6. So we'll start at 0. We'll go to 6. And we had a critical value at h equals 3. We just need to look at the sign of a prime on both of these intervals. And remember what a prime was. A prime is negative 2 times h plus 6 times h minus 3. And we're dividing that by this square root. So I list the factors of a prime down here. That square root is always positive. Oops, should be a minus here, except for when it's 0, and it's only 0 at 6 and negative 6. So this is positive. Negative 2 is negative no matter what h is. Remember, this is a number line of h values. And I've eliminated this and eliminated that because it's not a part of my domain for this problem. When h is between 0 and 3, h plus 6, it's a positive number plus 6 is positive. Another positive number plus 6 is positive. Over here, h minus 3, that actually changes signs at h equals 3, so we need to test the sign of h minus 3 on this side and this side. So pick any h value you want, maybe 1. 1 minus 3 is negative 2, so that's negative. And then you can pick any h value you want on this interval and use that as a test value. Try h equals 4. 4 minus 3 is 1, which is positive. So we have a negative times a positive times a negative over a positive. Negatives cancel in pairs, so that's a positive a prime. And then negatives cancel in pairs here as well. We have a negative. So we've got our sign chart. We know a prime is positive. That means a, the original function, is increasing on that interval. And the original function a is decreasing on that interval. So the function goes from increasing to having 0 slope to decreasing So that means we must have a relative max at the top at a or h equals 3. So a of 3 is a relative maximum. And you can see that if this is our domain, if it starts low and then it goes high and then it comes back down low again, that has to be the absolute max. So it turns out to be the absolute maximum of the function on the implied domain. And that's what we wanted. We wanted to find the maximum value of the area. So they said h equals 3. Okay, so what does that mean? That means my triangle looks like this. It doesn't look like it's halfway in between, just because my graph is not perfect. Okay, that's my triangle. There's 6, and we go down 3. Should be halfway in between. And the area is 1/2 base times height. This height is 9. So it was 6 plus little h. So 6 plus 3 is 9. And the base, no, it's been a while since we calculated it. It was 2 times the x value, and that was 2 times the square root of 36 minus h squared. Because this point was x and the negative square root of 36 minus x squared. And the base is x plus x, so that's 2x. So this is actually 2x when we're on this circle. Or actually, that's one way of writing it. Or in terms of h, the y value is negative h here. And the x value is 36 minus h squared. So when h is 3, y will be negative 3. And the x value will be 36 minus the square root, or 36 minus negative 3 squared, and then we take the square root. Which is the same thing we get when we just substitute in h equals 3 here. So we've got 36 minus 9. That's 27. Square root of 27. It's the square root of 9 times the square root of 3. Square root of 9 is 3. So we have 2 times that 3. It's going to give us a 6, and the square root of 3 can't be simplified. So we've got 1/2 base times height. So we'll have 1/2 of 9 times 6 root 3. And 1/2 goes into 6 3 times, so we get 27 root 3. That's the absolute maximum of the area of that triangle that can be inscribed in that circle. Okay, so that was part A. We were asked to solve by writing the area as a function of h. Now we want to solve this problem by writing the area as a function of alpha. I found this a little bit harder myself. There might be a more elegant way than the way I'm about to show you, but yeah, writing this as a function of alpha writing the area of this as a function of alpha was tough. It was tough for me. But we can do it, and I'll show you how. Okay, so this is alpha. And this is an isosceles triangle. So I know that this angle plus this angle plus this angle has to be 180, and these two angles have to be the same. So with that, I could find these two angles in terms of alpha. We could also remember that we're taking this angle at the top and we're splitting it into two pieces. So that forms two right triangles. If this is a right triangle and alpha is that angle, like let's say alpha was 30, well then that angle would have to be 60, because this angle plus this angle has to be 90 for that angle to be 90. So this is 90 minus alpha. Of course, we'll convert to radians later because we're in calculus class. I still think in degrees though. So we're right here. And now our goal is to write the area of this triangle in terms of alpha. But remember, if I'm writing the area of this triangle as a function of alpha only, that's not going to be very helpful, because of all of the similar triangles. Once I know what alpha is, let's say alpha is 15 degrees, well, I could make all those side lengths longer and all those side lengths longer. Like there are lots and lots of triangles that have the same alpha. So we have to write our area of the triangle in terms of alpha, but it has to somehow take into account the fact that these endpoints are on this circle of radius 3. So remember, x squared plus y squared is equal to 36. I said circle of radius 3, I meant circle of radius 6, sorry. X squared plus y squared is 36 when we're on this circle. And this point is at x equals 0, y equals 6. And this point is at an xy pair that satisfies the equation of that circle. We want to keep that in mind. You don't have to use this again, but you can also remember that h was that value. And h is a distance, and y is going to be the negative of that distance. So if h happened to be -3, like we got in the last part, or if h was 3, then y would be -3 down here. So you want to keep all of that in mind. Okay, so we need to write our area, which is 1/2 base times height, as a function of alpha. Well, if this is my base, excuse me, that's the base, then this side right here, it's my x value, that's 1/2 of that. And the height, that's that distance from here to there, well, that's that distance. So if I'm trying to get 1/2 base and height in terms of alpha, probably the easiest way to do it is to use a trig identity. We know that tangent is opposite over adjacent, and h is adjacent to alpha, and 1/2 of b, 1/2 of the base, is opposite alpha. So we've got tangent is opposite over adjacent. Opposite side is 1/2 b, adjacent side is h. So we can solve that for 1/2 b. And so now I can replace 1/2 b with h tangent theta. So I've got A, that's the area of my triangle, is h tangent theta times h. So that's h tangent alpha. I'm sorry, I'm using the wrong angle. Okay, so area is h squared tangent of alpha. Now we just need to find h as a function of alpha, provided that we are on this circle. When I first tried to solve this, I was engaging in a lot of circular reasoning, no pun intended. Everything kept canceling out. I kept getting trig identities. And the reason was I wasn't considering the fact that I'm inside this circle of radius 6 that has the equation x squared plus y squared equals 36. So we have to use this equation somehow. So we need h as a function of alpha. when we're on this circle. And this, it looks kind of like h is that hypotenuse there. It's not. H is this height. It's this vertical distance right here. I'm sorry for the way that that looks. Let me just write it on that side. Okay. Well, one thing that we know from what we did in the first section is that the y value over here at this point, xy, that y value is equal to the negative h. It's the opposite of h. And x, I'm just going to leave as x for right now. So y is negative h. And remember, h plus 6, that has to be capital H. So I can solve this for lowercase h by subtracting 6 from both sides. And that means that y can be written as the opposite of that. So we have y equals 6 minus h. So I've got y in terms of h right here. That's good. I'd also like to have x in terms of h. Well, we actually already have x in terms of h. Remember, x is the same as 1/2 of the base. X is that distance there. That is x. So when I am on this little line segment, my x value is equal to h tangent of theta. I keep saying theta, h tangent of alpha. And my y value is this. Now, since this point is on the circle of radius 6, this satisfies the equation of the circle and this satisfies the equation of the circle. I can substitute these here and I can get h in terms of alpha by simplifying that equation. So I've got x squared plus y squared equals 36. So I needed x in terms of h and alpha, and I needed y in terms of h and alpha. So I can get an equation that involved h and alpha, and also brought into the problem solving the fact that x squared plus y squared equals 36 when we're on this circle. So I'm replacing x with h tangent of alpha. I'm replacing y with 6 minus h. Just forgot to square those. Now I can simplify this and solve for h as a function of alpha, which is exactly what we need right here in order to be able to solve this problem. Excuse me. There might be a more elegant way. I have a feeling there's a more elegant way to do this, but I haven't thought of it yet. Okay, so we want to write h as a function of alpha. So I've got a product here, and I'm squaring it, so I can square the first factor and second factor separately. This 6 minus h, that's 6 minus h times itself when you're squaring it. It can be written that way, and then you would distribute or FOIL either way. 6 times 6 is 36. Outer times outer is negative 6h. Inner times inner is another negative 6h. So that's negative 12h plus h squared equals 36. Okay, and we can subtract the 36 from both sides. So we get 0 over here. And that looks like 12. It looks like 126, but that should be 12h, sorry. Now notice we've got an h squared tangent squared alpha and an h squared. We can group those together as well and factor out the h squared. Remember that tangent squared plus 1 is secant squared of the same angle. And now I can solve this equation for h as a function of alpha. Well, first, in order to do that, the first thing I would do is I'd factor that. These two terms have an h in common. And if this times this equals 0, either the first factor equals 0 or the second factor equals 0. Now h equals 0, that's really not of interest to us. We're trying to find an area with area is 1/2 base times height, and that capital H is the height of our triangle. We can't have a height of 0. That's not going to work out. So h equals 0 is a solution to that equation, but it doesn't make sense for our problem. So we can rule it out. Over here, you've got h secant squared alpha minus 12 equals 0. So you can add 12 to both sides. Divide both sides by secant squared. And remember, secant is 1 over cosine. So that's cosine squared alpha. And now I've got h in terms of alpha, and I can substitute that in over here, and I'll have area as a function of alpha. And that area as a function of alpha will take into account the fact that xy is a point on this circle. So my area was h squared tangent of alpha, and h turned out to be 12 cosine squared alpha. So now my area is a function of alpha, and I've got 144. Cosine squared squared is cosine to the 4th. You can optimize this, or you could simplify a little further. I probably would, or I will. Tangent is sine over cosine. So one of those cosines will reduce, and we'll have that. Now at this point, you can use trig identities to rewrite this if you want to, or you can just start differentiating, because we want to maximize area as a function of alpha. And again, we want to find the maximum area. We should get the same result that we got when we found area as a function of that distance, lowercase h, in part A. So if I want to optimize this, we did the hard part, which was finding area as a function of alpha. And now that we've done that, we want to optimize it. So we want to find the critical points of A by computing the first derivative, setting the first derivative equal to 0, and solving for alpha. And of course, we only want to include those values of alpha that are in the implied domain that makes sense for our problem. Okay, so let's do this. I'll factor out that 144, and I'll use the product rule for this. That's my first function, and that's my second function. So we're going to have derivative of the first with respect to alpha times the second, undifferentiated, plus derivative of the second with respect to alpha, which happens to be cosine of alpha, times the first, which is cosine of alpha cubed. Now remember, if you have cosine cubed alpha, that's the same as cosine of alpha quantity cubed. So that's really a function cubed. So when I'm taking the derivative of that, it makes the most sense to use the chain rule. So we still have the 144 here. And then over here, we've got derivative of something cubed is 3 times that function that we started with squared. times the derivative of the inside by the chain rule. Derivative of cosine is negative sine. And we're multiplying by another sine of alpha over here. And then I've got 4 cosines multiplying each other here, so that's cosine of alpha to the 4th. Cosine to the 4th of alpha. And then over here, I've got sine times sine is sine squared alpha. And that negative I'll pull out front. So we're here now. In order to solve this, we can factor and solve for alpha. Yes, I need to set this equal to 0 first, then I'll factor and solve for alpha. I look at these two terms, I see ask myself, what do they have in common? Well, this has a cosine squared in it, and that has a cosine squared. Remember, that's cosine times cosine, that's cosine times cosine times cosine times cosine. So I can take out a cosine squared from both of those. We're gonna factor that out. And then we're left with a negative 3 sine squared alpha. And I took out cosine squared, so there are 2 more cosines left. The only way this product is 0 is if one of the factors is 0. Cosine squared alpha equals 0 when cosine of alpha equals 0. And the only time that happens is when, well, there are infinitely many times this happens algebraically, but there are infinitely many solutions to this equation, but there's only one that even gets close to making sense for our problem. These angles inside this triangle have to be between 0 and 180. And then they have to add to be 180. So none of these angles can be 180 degrees. So yeah, our angle has to be between 0 and pi radians. That means our angle would have to be pi over 2 or 90 degrees. But then think about it. Alpha is actually not this angle. It's half of that angle. If that one's 90, that one would be 90 as well. And so that'd be 180 degrees. So that can't be, so this is not, that's not going to be the case. I can't have one angle in my triangle I can't have that angle to be 180 degrees and have a triangle. Then it would be a straight line, actually. So this one doesn't make sense for our problem. But we do see that we've got some restriction on alpha. Alpha has to be between 0 and 90 degrees for this to even be close to making sense. Can't equal 90, but it could be less than 90. So that was 0 here, which doesn't make sense for our problem, or we could have this factor equals 0. And I will subtract cosine squared from both sides, multiply both sides by -1. Let's divide both sides by sine squared alpha. So we get 3 equals cotangent squared alpha. Or let's do 1/3 equals tangent squared, because I still think in terms of sine, cosine, and tangent, not so much cotangent. And then let's take the square root of both sides. We don't really need the plus or minus because of what alpha is. I know I've got an angle here and it's between 0 and 90 degrees. So tangent of alpha would have to be 1 over square root of 3. Well, the only way that happens, that's opposite over adjacent is 1 over square root of 3. That only happens in a 1, 2 square root of 3 triangle that looks like this. So alpha has to be 30 degrees, or better yet, let's change to radians. That's 1/6 of 180 or pi over 6. Okay, so we've got a critical point. It's pi over 6 or 30 degrees. And we need to determine whether that critical point corresponds to a minimum or a maximum. Notice that when we're finding critical points, we would also have to look at this and see if it's ever undefined, and it's not undefined ever. This is the only critical point that we have on our implied domain of 0 to 90 for alpha, or 0 to pi over 2 for alpha. So we need to determine if that corresponds to a minimum value or a maximum value of our function. There are a couple of ways we can do that. We can make a sign chart for this product. I think I'd rather do something else, honestly. I think I would rather take the second derivative of this function right here, take the derivative again, and then substitute in pi over 6 and see if the graph is concave up or concave down. So let's do that. We're finding a double prime now. That's the derivative with respect to alpha of something. And our function was 144 negative 3 cosine squared alpha sine squared alpha plus cosine to the 4th of alpha. Oops, it's positive 144. Okay, so we're taking the second derivative, and then we're going to substitute in our critical value, see if the graph is concave upward there or concave downward there. Take out the 144. And for this part, we'll use the product rule. I'll call that my first function. Let's say we have the derivative of the first with respect to alpha, and I'm going to write that as cosine of alpha squared times the second undifferentiated plus derivative of the second with respect to alpha times the first undifferentiated all of that is being multiplied by that 144, and the 144 multiplies the derivative of cosine to the 4th of alpha as well. So I'll have a 144 down here. And the derivative of this requires the chain rule, because remember, that is cosine of alpha all raised to the 4th. The derivative of a function raised to the 4th power is 4 times that function cubed. The derivative of the outside evaluated at the inside. And then, of course, we multiply by the derivative of the inside with respect to alpha, which happens to be negative sine of alpha. Okay, and let's compute these derivatives. This one requires the chain rule. We've got negative 3 times a function squared. The derivative of that is negative 6 times the function to the first. And we multiply by the derivative of the inside. Derivative of cosine of alpha is negative sine of alpha. Over here, I've got a function squared. Derivative of a function squared is 2 times that function to the 1 less power, but 2 minus 1 is 1, times the derivative of the inside. Derivative of sine is cosine. So this looks pretty bad, but it's actually not too bad at all. I've got a negative times a negative. That's a positive 6. Cosine times sine. I've got 2 sines here and 1 more sine, so that's sine cubed of alpha. And I've got a negative 6 here, sine of alpha times cosine cubed alpha. And then over here, I've got a negative 4. I factored out the 144. Negative 4, and I've got cosine cubed times sine. And I've got a cosine cubed times sine here and a cosine cubed times sine there, so I could combine like terms. So I've got minus 10 of those. I guess we could factor things out if we wanted to. Factor out a sine and a cosine. Actually, I think I'm going to leave it alone. Remember, what we want now, the reason we took the second derivative was so that we could use the second derivative test. We want to substitute in alpha equals pi over 6 and see what we get. So we have 144 times 6 times cosine of pi over 6 times sine of pi over 6 cubed minus 10 times sine of pi over 6 times cosine of pi over 6 cubed. So let's just look at a triangle. If this is 30 degrees, opposite the 30, and that's the same as pi over 6 radians, is a 1. This is a 1, 2 square root of 3 triangle. So sine of that angle is 1 over 2. So sine of alpha is 1/2. So I have a 1/2 cubed here and a 1/2 over here. And cosine of alpha is adjacent over hypotenuse. So it's square root of 3 over 2. Okay, so that is our second derivative. We just need to see if it's positive or negative. So I've got 144 times 6 root 3 over 2 times 1/8. And here 2 goes into 10 5 times. And we have minus 5 times this cubed. Square root of 3 cubed is 3 times the square root of 3. And the 2 cubed is an 8. So I've got 3 root 3 over 8 minus 15 root 3 over 8. Well, that's negative. What does that tell us? That tells us that the graph is concave downward at pi over 6. And remember, the slope was 0 at pi over 6. So that means that A evaluated at pi over 6, I wrote pi over 3, pi over 6 is a relative maximum. And since it's the only critical point, it actually turns out to be the absolute maximum of the function. So what is that saying? It's saying I'm going to try to do a good job. Oh, I keep making these horrible looking circles. It's just getting worse and worse. Sorry, guys. What does that mean? Well, if alpha equals pi over 6, that's 30 degrees. That means this angle at the top is 60 degrees. And if this is an equilateral triangle, that means this is 60 and this is 60. And I think that makes a lot of sense. It makes sense that that would have to be 60 and that would be 60 and that would be 60. Okay, now they asked us to find the area of the largest isosceles triangle that can be inscribed in the circle of radius 6. Well, so I need to actually evaluate that area at pi over 6. Well, it's been a while. Where's that original area formula? Area was this, 144 times cosine cubed of alpha times sine of alpha. This is cosine cubed, and cosine is square root of 3 over 2. And sine of alpha is 1/2. So I end up with 144 times 3 root 3 over 8 times 1/2. So 2 goes into 144 72 times. And then 8 goes into 72 9 times. So we end up with 27 root 3 square units, which is exactly what we got using the other method. Now, part C of the question says, identify the type of triangle of maximum area. We can see that if alpha is 30, that's 30 and 30 is 60, and then all these angles are the same. So for part C, we'll just say the triangle of maximum area happens to be an equilateral triangle. And I think we all knew that. I don't know about you. Feels like we just did some calculations that confirmed that what we suspected was true. I wrote equilateral area, equilateral triangle. There we go. Now there might be a more elegant way to solve that, but that's the way I solved it. Let me know if you have any questions, guys.